This last video for chapter 5.2 is going to be super duper short. It's just introducing a different value for your base. So welcome to a new constant. It's kind of like a pi number. It's the number e. E is a very special number in mathematics. In fact, it was found by Leonard. Now, there's controversy. I don't know whether it's Euler or Euler. Some of the things I find online say you're supposed to pronounce this Euler. Some people say it's supposed to be Euler. I don't know. Whatever. It's a dude who came up with the number e. It's a decimal representation of a number that doesn't terminate or repeat, just like pi, and it's constant and it's used a lot in nature. So instead of me explaining what it is, I'm going to let a video explain it. So just 1 second. All right, so hopefully this is going to work.
I'm going to talk about E, the big famous constant E. Okay, it's one of the famous mathematical constants, one of the most important. It goes along with pi and, I don't know, golden ratio and a square root of 2. There are constants in maths that are the most important constants. And E is one of those constants. So E is an irrational number and it's equal to 2.718281828 something something something. The problem with E is it's not defined by geometry. Now pi is something that's defined by geometry, right? It's the ratio of a circle circumference and its diameter, and it's something the ancient Greeks knew about. And a lot of mathematical constants go back to the ancient Greeks, but E is different. E is not based on a shape. It's not based on geometry. It's a mathematical constant that is related to growth and rate of change. But why is it related to growth and rate of change? So let's look at the original problem where E was first used. So we're going to go back to the 17th century, and this is Jacob Bernoulli, and he was interested in compound interest, so earning interest on your money. So imagine you've got £1 in the bank, and you have a very generous bank, and they're going to offer you 100% interest every year. Wow, thanks a lot, bank. So 100% interest, so it means after 1 year, you'll have £2. So you've earned £1 interest and you've got your original pound. So you now have £2. What if I offered you instead 50% interest every 6 months? Now, is that better or worse? Well, let's think about it. Okay, you're starting with £1 and then I'm going to offer you 50% interest every 6 months. So after 6 months, you now have £1.50. And then you wait another 6 months and you're earning 50% interest on your total, which is another 75p. And then you add that on to what you had, so it's £2.25. Better. It's better. So what happens if I do this more regularly? What if I do it every month? I offer you 1/12 interest every month. Is that better? So let's think about that. So after the first month, it's going to be multiplied by this. 1 plus 1/12. So 1/12, that's your interest. And then you're adding that onto the original pound that you've got. So you do that, that's your first month. And then for your second month, you take that and multiply it again by the same value. And then your third month, you would multiply it again and again. You actually do that 12 times in a year. So in a year, you would raise that to the power 12 and you would get £2.61. So it's actually better. In fact, the more frequent your interest is, the better the result. Let's start with every week. Okay, so if we do it for every week, how much better is that? Okay, what I'm saying is you're earning 1/52 interest every week. And then after the end of the year, you've got 52 weeks and you would have £2.69. So it's getting better and better and better. In general, you might be able to see a pattern happening here. In general, it would look like this. You'd be multiplying by 1 plus 1/n to the power n. Hopefully you can see that pattern happening. So here n is equal to 12 if you do it every month, 52 if you do it every week. If you did it every day, it'd be £1 multiplied by 1/365 to the power 365, and that's equal to £2.71. And so it would get better if you did it every second or every nanosecond. What if I could do it continuously? Every instant I'm earning interest, continuous interest. What does that look like? That means if I take this formula here, 1 plus 1/n to the n, I'm going to n 10 to infinity. That would be continuous interest. Now, what is that? What is that value? And that's what Bernoulli wanted to know. He didn't work it out. He knew it was between 2 and 3. So 50 years later, Euler worked it out. Euler, he works everything out.
Him or Gauss?
Yeah, it's either Euler or Gauss. Say Euler or Gauss, you're probably going to be right. And the value was 2.71828282845, and so on.
We were pretty close when we were doing it daily, weren't we? It was already 271 at daily.
You're right. We're getting closer, weren't we? We're getting closer and closer to this value. So already we're quite close to it. If you did it forever, though, of course, you would have this irrational number. Now, Euler called this E. He didn't name it after himself, although it is now known as the Euler constant.
Why did he call it E then?
It was just a letter. Yeah, he might have used A, B, C, and D already for something else, right? So you use the next one.
Bit of a coincidence.
It's a lovely coincidence. I fully believe that he's not being a jerk here, naming it after himself, but it's a lovely coincidence that it's E for Euler's number.
Would you have called it G if you discovered it?
I would not have called it G. No, I would have hoped somebody else would have called it G, and then I would have accepted that. Euler proved that this was irrational. He found a formula for E, which was a new formula, not this one here, a different formula, and it showed that it was irrational. I'll quickly show you that. He found that E was equal to 2 plus 1 over 1 plus 1 over 2 plus 1 over 1 plus 1 over 1 plus 1 over 4 plus 1 over 1 plus 1 over 1 plus 1 over 6 plus, and this goes on forever. This is a fraction that goes on forever, continuous fraction, but you can see it goes on forever because there's a pattern, and that pattern does hold. You've got 2, 1, 1, 4, 1, 1, 6, 1, 1, 8. So you can see that pattern goes on forever, and if the fraction goes on forever, it means it's an irrational number.
So I figured I would just stop that video there. If you're interested in the rest of the video, you can totally watch the rest of it. He goes on to kind of graph it, but he starts talking about factorials, and I was like, that's too much. But what I wanted you to get from that, not just from my point of view, but from someone else's point of view, is that Euler's number is this naturally occurring phenomenon with continuous, and here's the key word, growth. So we can look at graphs with a base E and notice that it is the exact same graph as a y equals 2 to the x, except that, when you get to x equals 1, you would have y equals 2.71 blah, blah, blah. When you have x is equal to 2, it would be y equals 2.71 blah, blah, blah squared. So we're never going to actually graph these, because it's really hard to graph accurately an irrational number. And so we would let a computer graph this for us, but we can look at it as the same shape of a y equals 2 to the x. It's an exponential growth graph where the growth is happening at a continuous rate. And that's what's important. When we get to applications of exponential functions, when we talk about growth and decay, we are going to always use a base E, because we're going to always be talking about things growing and decaying at a natural growth rate. So y equals e to the x has an asymptote at y equals 0. It has a domain of negative infinity to infinity. It has a range of 0 to infinity. It is an increasing graph. It is a growth graph, although it can be made a decreasing graph. If you wanted it to decrease, you would do y equals e to the negative x, which is what we're going to do. That will be when we have a natural decay. And then the y-intercept, of course, if you put even an irrational number to the exponent 0, you will have a y-intercept at 0, 1. So for today, all we're going to do, we used to graph these, but I was like, that is dumb because we can't graph an irrational number exactly. So all we're going to do in this lesson is just introduce that concept of E. So I was looking for my calculator, and we're going to practice finding it on your calculator. So let's just see. Maybe I was going to pull up my calculator here, but maybe what I'll do is just pull up my Desmos graphing calculator. So if I want to find the value of E on my calculator, it should exist somewhere. Oh, there's mine. So if I plug in the value of E, now I can just type E, and it'll come up as 2.71828 blah, 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 as many decimal places as your calculator will show. Your calculator might make you do e to the exponent 1. So again, I have just an e button, but most calculators have this e to the x button because they're like, okay, well, what exponent do you want to put on e? And so if I put in an e to the 1, I can get 2.718, so on and so on and so on. So if I go back to the note right here, I want you to put e to the 1 is, now I've forgotten that number, 2.718. Now we're going to go to 4 decimal places, so we're going to round it to 2.7183. And then just purely for practice, you're then going to take your calculator and you're going to plug in e to the, what did it say? Sorry, it closed on me. E to the negative 0.23. So you're going to put into this exponent negative 0.23. And we get 0.7945. Can I remember that? 7945, 7945. 0.7945. Now again, just to emphasize, a negative exponent does not mean you're going to get a negative answer. It means that it's making it into a fraction and it's decaying instead of growing. So the number's getting smaller instead of the number getting bigger. All right, welcome to E.